Okay, let's dig into this. What exactly is nothing?
Yeah, it sounds like such a basic question, doesn't it?
Right. Deceptively simple. But the more you think about it, the harder it is to pin down. I mean, everywhere you look, there's always something.
That's true. It feels like existence, some kind of stuff, is just the default state.
Well,
Our intuition screams against true emptiness.
totally. Wrapping your head around absolute nothingness. It's tough.
It really is.
And this isn't just, a philosophical mind game. Think about a box. If you could somehow take everything out.
Everything, like all the air, dust,
Yeah.
every last atom.
Exactly. What's left? Just empty space? Is that nothing? Or does emptiness itself have, properties?
That's the million-dollar question, isn't it? Is the absence of stuff a true void, or is it something else? And like you said, it's not abstract.
Right.
Emptiness dominates the universe. Even inside atoms, the stuff we're made of, it's mostly empty space.
So that's our mission for this deep dive then, to really explore this void, vacuum, emptiness, nothing, whatever we call it.
And explore the kind of mind-bending idea that understanding it might unlock the universe's biggest secrets.
Maybe even our own existence, as we'll get to.
Yeah, because when you zoom out,
Yeah.
the whole universe, everything we see, the theory is it came from nothing almost 13 billion years ago.
It's staggering.
It really is.
Okay, so where do we start? Historically, this idea of nothing, it caused problems, right?
Oh, big time.
Uh.
For over 1,000 years, Aristotle really dominated the thinking here.
The ancient Greek philosopher.
That's the one. And he was not a fan of nothingness. He saw all sorts of logical problems, paradoxes.
Famously saying nature abhors a vacuum.
Exactly. The idea that the world actively resists emptiness. And, everyday stuff seemed to back him up.
Like a drinking straw. That's a classic example, isn't it?
It is. You suck the air out, more rushes in, block the bottom, and suck.
The straw collapses.
Right. It looks like the universe is fighting you, trying to prevent that void.
And then there's the trick where you pinch the top after taking a sip, and the liquid just hangs there, defying gravity, it seems.
All these little observations really cemented that idea for centuries.
Yeah.
Making a vacuum. Impossible.
But then things started to shift in the 17th century.
Yeah, you start seeing the first little cracks in that Aristotelian view.
Yeah.
People started noticing exceptions, almost like you could trick nothingness into existence.
How? Through experiments.
Exactly. Less philosophy, more hands-on testing.
Yeah.
Evangelista Torricelli, his work was absolutely pivotal.
What did he do? It sounds simple, but...
It does. He filled a glass tube with mercury, sealed one end, and then flipped it upside down into a dish of mercury.
Okay.
And the mercury level in the tube dropped. It didn't empty completely, but it left a space at the top.
An empty space.
An airless space.
Right.
He'd created the first real sustained vacuum. And crucially, he showed the atmosphere has weight.
Ah, so that's why the straw collapses. It's not nature abhorring a vacuum.
It's the weight of the air outside, pushing in.
Yeah.
Atmospheric pressure.
Right.
And in Torricelli's tube, the weight of that mercury column balanced the air pressure. His quote is great. We live at the bottom of an ocean of air.
That really changes things. Air isn't just nothing, it's a substance.
A substance with weight, with pressure. It's a huge conceptual leap.
I bet that wasn't easy to accept, challenging centuries of thought like that.
Oh, definitely not. There was a lot of disbelief, resistance. But then Blaise Pascal took it further.
Pascal, what did he add?
He did a really elegant experiment. Took one of Torricelli's mercury tubes up a tall tower in Paris. And as he went higher, the mercury level in the tube dropped even more.
Meaning less air pressure higher up.
Exactly. Less of that ocean of air pressing down. It proved air pressure decreases with altitude.
So the big realization from Torricelli and Pascal is what? That nothing is the default.
Pretty much. That emptiness, the void, is the normal state of the universe. Earth's atmosphere is just this thin, fragile layer. We're a tiny speck in a vast silence.
Which naturally leads to, okay, if we can make a vacuum, what is it? What are its properties?
Right. Once you can create it reliably on Earth, the scientific curiosity just takes over. What can you do with this nothingness?
And they started testing things, right? Like putting a bell in a vacuum chamber.
A classic experiment. Ring the bell, you see it vibrating.
But you hear nothing. Sound needs air or some medium. Makes sense.
And this was the puzzle. You could still see the bell. Light was getting through the vacuum.
Huh. So if light travels through it, it can't be completely empty.
That was the conclusion they drew. There must be something filling all of space, something invisible that carries light waves.
Like air carries sound waves.
Exactly. They called it the luminiferous ether, the light-carrying stuff.
So they finally make nothing, only to decide it isn't really nothing after all. We're back to square one, sort of.
In a way, yeah.
Yeah.
It brought back that idea that true absolute emptiness just couldn't exist. Light needed something to travel through.
Because light was understood as a wave back then.
Primarily, yes. And waves, as far as anyone knew, needed a medium. Water waves need water. Sound waves need air. So light waves needed the ether.
But this ether, nobody could find it.
That was the problem. It was supposed to be everywhere, filling the entire universe, but it was completely undetectable, immeasurable, ghostly stuff.
Which brings us to a really famous experiment, doesn't it? Michelson-Morley.
Absolutely. Late 19th century, right here in the US, Albert Michelson, who actually became America's first Nobel laureate in physics.
He led this effort. What were they trying to do?
They had this really clever idea. If the ether exists and Earth is moving through it,
Like a ship through water.
exactly, then we should feel an ether wind. Or rather, we should be able to detect its effect on the speed of light.
How would that work?
Well, light traveling with the ether wind should seem slightly faster, and light traveling against it should seem slightly slower, relative to us on Earth.
Like running with the wind versus running into it.
Precisely. So Michelson designed this incredibly sensitive device.
State of the art for the 1880s, I imagine.
Oh yeah, beam splitters, mirrors, a detector, all mounted on this massive sandstone block floating in mercury to damp out vibrations. Super precise.
And they were looking for
An interference pattern. If light beams traveled slightly different distances or speeds because of the ether wind, when they recombined, they'd interfere, creating a specific pattern. A dark spot, they thought.
But the difference they were looking for must have been tiny, right? Light is so fast compared to Earth's speed.
Incredibly tiny, like 1 part in 100 million. The precision needed was just astronomical. Many thought it was impossible.
And the result?
No matter how they turned the apparatus, no matter which direction they measured, nothing. The speed of light was always the same.
No ether wind.
No sign of it whatsoever.
How did they react? That must have been shocking.
It was. But their initial reaction, because they were so convinced the ether had to exist, was that their experiment had failed somehow.
They thought they were wrong, not the theory.
Pretty much.
Yeah.
It took a while for the real implication to sink in.
Which was, if there's no ether.
Then light doesn't need a medium. It can travel to perfectly empty space.
Wow, that completely changes the game.
It does. And then Einstein comes along in 1905.
And explains how light does it.
Yes. He showed light isn't just a wave in a medium. It's this self-propagating disturbance of electric and magnetic fields. It can travel through a complete vacuum.
And that led to his theories of relativity, because the speed of light is constant.
Exactly. It became a fundamental constant of nature, not relative to some invisible ether.
So the Michelson-Morley result really pointed towards the vacuum being truly empty.
It certainly seemed that way. Maybe nothing was just nothing after all.
But I sense a but coming. You said if only it were that simple.
Right, because the story gets even weirder in the century after Michelson-Morley.
How so?
Well, partly driven by technology, actually. Making vacuums became really important for industry.
Light bulbs, TV tubes.
Vacuum tubes for electronics, all sorts of things. And this improved vacuum technology became an amazing tool for physicists.
Because they could study things without air getting in the way.
Precisely. It helped them discover X-rays, the electron.
Right.
Rutherford used it to figure out the structure of the atom. And all this paved the way for quantum mechanics.
Okay, here we go. Quantum mechanics. This is where empty space stops being simple, right?
Completely. The quantum world is just fundamentally different. It's not about certainty, it's about probabilities, uncertainty.
And Heisenberg's uncertainty principle is key here.
Absolutely key. And kind of troubling for the idea of a truly empty, inert vacuum.
Remind us what it says again?
Basically, that nature has limits. You can't know certain pairs of things about a particle perfectly at the same time, like its exact position and its exact momentum.
The memory stick analogy you mentioned. A sharp photo means clear position, blurry motion.
Yeah, or a clear video shows the motion, but the position at any instant is fuzzy. There's a trade-off. Know one precisely, the other becomes uncertain.
Okay, position and momentum. How does that relate to empty space?
Well, the principle also applies to other pairs, like energy and time.
Energy and time.
Yes. The more precisely you know the energy in a tiny region of space, the less precisely you know for how long that energy measurement is valid, and vice versa.
Okay, I think I see where this might be going.
Right. So if you look at incredibly short moments in time, tiny fractions of a second, in very small volumes of space,
The uncertainty in energy gets big.
it's huge. So huge, in fact, that for a fleeting instant, enough energy can sort of pop into existence from nothing.
From the vacuum itself.
From the vacuum. Enough energy to actually create particles.
Whoa.
But here's the catch. They have to disappear again almost instantly. It's like borrowing energy from the universe, but you have to pay it back fast.
So particles can just appear out of nowhere as long as they vanish quickly.
Essentially, yes. Think of it as quantum fluctuations.
Yeah.
The vacuum isn't empty and quiet. It's fizzing with activity.
Alive with virtual particles. Is that the term?
That's the term. Fleeting packets of energy constantly popping in and out of existence, allowed by Heisenberg's uncertainty. Borrowing energy, paying it back.
So the vacuum is this dynamic, seething something, not nothing.
Not nothing at all. And this leads us to Paul Dirac.
Another giant of physics. A bit unusual, though.
Brilliant, but yes, famously reserved, very focused few words. They joked about a unit of shyness called the Dirac.
But he had this visual way of thinking about physics.
Very much so. Came
Yeah.
from his background in math and technical drawing,
Yeah.
and that was crucial for his big breakthrough in 1928.
What was the problem he tackled?
The big challenge then was making Einstein's relativity work with quantum mechanics, especially for describing the electron. They didn't fit together properly.
And Dirac managed it.
He did. He came up with this incredibly elegant equation, the Dirac equation, that described electrons perfectly, incorporating both relativity and quantum mechanics.
You mentioned he saw equations visually, like storytelling.
Yeah, he apparently loved the visual narrative of 2001, A Space Odyssey. His equation was like that compact, beautiful, but with hidden depths. He even said it was smarter than he was.
Because it predicted something unexpected.
Exactly. It predicted another particle, just like the electron, but with opposite properties, specifically opposite electric charge.
The anti-electron, the positron.
The positron, yes. The first piece of antimatter predicted.
And antimatter, it's like a mirror image of regular matter.
Pretty much. Antiprotons, antineutrons.
Yeah.
You could theoretically build anti-atoms, anti-U.
But the key thing is what happens when matter meets antimatter.
Annihilation. They wipe each other out completely, converting all their mass into pure energy. According to Yves Cissai, bang, gone.
Okay, how does this connect back to the vacuum and Heisenberg?
Dirac's theory gave a mechanism for those quantum fluctuations. The particles popping out of the vacuum could be particle-antiparticle pairs.
Ah, an electron and a positron, say.
Exactly. They could borrow energy from the vacuum, exist for that tiny fraction of a second allowed by Heisenberg.
And then annihilate each other, paying back the energy.
Precisely. So that constant fizzing isn't just random energy. It's this dance of virtual particle-antiparticle pairs being created and destroyed constantly.
So the vacuum is redefined again. Not just empty, not just fluctuating energy, but a sea of potential matter and antimatter pairs.
That's the picture from quantum field theory, which refined Dirac's ideas. These virtual particles are flickering in and out of existence everywhere, all the time.
It sounds wild. There's actual proof? Can we see this happening?
Not directly. They're virtual for a reason they don't last long enough, but we can see their effects. Willis Lamb's experiment was crucial here.
Inside an atom.
Yes. He showed that an electron orbiting an atom doesn't follow a perfectly smooth path. It has this tiny, tiny wobble.
Like a plane hitting turbulence.
That's a great analogy. The electron is being subtly jostled by these virtual particles popping in and out of the vacuum around it.
How on earth did they measure that? It must be incredibly small.
Unbelievably small. It took incredibly precise experiments using lasers to probe the energy levels of atoms in vacuum chambers.
You mentioned the scale. If the wobble was apple-sized.
The vacuum chamber would have to be trillions of miles across.
Yeah.
Hundreds of times bigger than the solar system. Just shows the finesse required.
And they saw the wobble.
They saw its effect. A specific shift in the electron's energy levels. A peak in their data that wouldn't be there if the vacuum was truly empty.
Wow. And did the measurement match the theory?
Astonishingly well. The predictions from quantum mechanics, based on Heisenberg and Dirac, match Lamb's experimental results to about 1 part in a million.
That's incredible agreement. Powerful evidence for this seemingly crazy idea of a fizzing vacuum.
It really is. It shows this nothingness has real, measurable consequences at the atomic level.
But the implications go even bigger, don't they? To the whole cosmos.
Oh, absolutely. This quantum weirdness of the vacuum isn't just relevant now. It seems to have shaped the entire universe from the very beginning.
How so? Back near the Big Bang.
Exactly. In the first tiny fraction of a second, the universe was smaller than an atom. Quantum rules weren't just important. They were the rules.
So those quantum fluctuations, the virtual particles, they were happening then too?
Yes. And the mind-blowing idea is that those incredibly tiny, submicroscopic fluctuations in the very early universe acted as seeds.
Seeds for what?
Seeds for structure. Tiny variations in density. As the universe expanded incredibly rapidly.
Inflation.
During inflation, yeah. Those minuscule density differences got stretched to enormous scales. Areas slightly denser started pulling in more matter gravitationally.
Leading to galaxies. Clusters of galaxies.
Eventually, yes. The entire large-scale structure of the cosmos we see today, the webs of galaxies, the vast, empty voids, it all traces back to those quantum jitters in the primordial vacuum.
Is there evidence for that? Sounds even wilder than the electron wobble.
There is. We have what's often called the baby picture of the universe, the cosmic microwave background radiation.
The afterglow of the Big Bang.
Right. And space missions like WMAP and Planck have mapped it incredibly precisely. It's not perfectly uniform. There are tiny temperature variations.
Hotter and colder spots.
Exactly. 20 fractions of a degree difference. And those variations are like fossils. Scars left over from those initial quantum fluctuations.
So we can literally see the imprint of quantum uncertainty on the scale of the entire universe.
We can. The pattern of those hot and cold spots matches the predictions based on quantum fluctuations being stretched by inflation incredibly well.
It's almost too much to grasp that the Milky Way galaxy started as a subatomic quantum blip in nothingness.
It's profound, isn't it? And there's one more cosmic link tied back to Dirac and antimatter.
Ah, yes, the matter-antimatter problem.
Right. The Big Bang should have created equal amounts of both from the vacuum energy.
But we live in a universe made of matter. Where did the antimatter go?
That's still a huge puzzle. The leading idea is near-perfect annihilation. As the universe cooled, matter met antimatter. Poof. Energy.
Almost perfect.
Almost. For some reason we still don't fully understand, there seems to have been a tiny asymmetry. For maybe every billion pairs that annihilated, one extra matter particle was left over.
Just 1 in a billion.
That's the estimate. A tiny imbalance.
Got over the scale of the early universe.
That tiny leftover fraction is everything. All the stars, all the galaxies, all the planets. You, me.
We're the leftovers, the debris from that cosmic annihilation.
In a very real sense, yes. We are the result of that slight imperfection, that tiny bit of matter that survived the great wipeout at the dawn of time.
Wow. So this whole journey, trying to understand nothing, it's taken us from Aristotle being uncomfortable with a vacuum
to realizing it's not empty at all, but this dynamic, energy-filled quantum realm.
And that this nothing actually dictated the structure of the universe and even led to our own existence as the leftovers of matter-antimatter annihilation.
It's an incredible story. Exploring the seemingly empty has revealed the deepest workings of reality.
It really makes you think. This profound link between the nothingness we started from and this vast, intricate universe we inhabit.
What is reality, really? Where did it all come from? Exploring nothing certainly gives you a lot to ponder.